Dear students, good morning. Today we'll continue coordination chemistry under paper 1. So in previous classes you have studied crystal field theory and splitting of d orbitals in octahedral, tetrahedral and square planar complexes. Today we'll move through limitations of crystal field theory. Very few of them are given here. The first one, according to CFT, the interaction between metal and ligand is purely electrostatic and cannot be said to be very realistic. Second point is CFT takes only the d orbitals of metal ion into consideration and it nowhere considers either p orbitals or s orbital of the metal ion. The third one is the theory fails to explain the behavior of certain metals which cause large splitting while some others cause small splitting. Even here also the theory fails to explain. Okay. Now with this we'll move on to the next one, that is color of the complexes. So the substance, if the substance or the complex exhibits color, means it has the property to absorb certain radiations from visible region of the spectrum. Okay, so the complex or the compounds which are having the tendency or say nature or the property of absorbing certain radiations from visible region, only those complexes exhibit color. Okay, for example, if the light falls on the complex, there are three possibilities. The complex may absorb whole light and appears, then it appears black. If it absorbs whatever the light falls on it, the whole light is absorbed by the complex, then that complex appears black. Okay. The second possibility, if the complex reflects or the transmits the whole light, whatever falls on it, if it does so, then the complex appears white. Okay. And the third possibility, the complex may absorb some of it and transmit the remaining light. Then that complex appears colored. Okay. So now during the splitting of d orbitals in complexes you have seen. So the d orbitals, they occupy different energy levels after splitting or after interacting with the metal ligand with the ligand, is it? So now when the complex or the complexes which are those complexes which are having partially filled d orbitals, and over that if they contain unpaired electrons, then only that complex is able to absorb certain radiations from visible light and exhibit colors. So this means the complexes which are having partially filled and unpaired d electrons, those complexes are exhibits color, or those complexes are colored complexes. And here the reason is the unpaired electrons which are present in d orbital, and if there is a smaller distance between the d orbitals, then that electron or those electrons will absorb the energy from the visible region and they jumps to the higher energy level, they shifts to the higher energy level by absorbing the light radiations, thereby that complex exhibits color. Now there are complexes which are colorless, and those complexes which are having completely filled d orbitals, a d10 state or d0 state. So those complexes, for example zinc amine, Zn 4 times, this is colorless. Any Zn plus 2 salts, they are colorless. Similarly copper plus 1 salts, colorless. Silver 1, colorless. Ti4, titanium 4, oxidation 4. So Ti3, this complex is colored because it is containing one electron and it absorbs green lights, and the complementary color, that means of the say complex, is violet. So similarly the cobalt salt absorbs D7 system, absorbs blue light and looks pink. And similarly, say the one more example, the cobalt COX4, that means halide, where X stands for halide, and which absorbs low radiation, that is of red light, and it appears blue. Okay, so the complexes appears colored only when they have partially filled d orbitals, and they contain unpaired electrons. Only those complexes are exhibit colors.